So up until now, we've always thought of the policy as like you choose what action you're going to take at some state. So you're at the state S. Do you choose to hit or stay? What is the best choice? That's a deterministic policy, right? So at some state, you always do the same thing. But the question is, why would you want to look at a random policy? So why would you want to say sometimes we'll hit, sometimes we'll stay? Why would that be a useful thing to do? All right, let's see what you guys said in the fun little word cloud, like we like to do. Oh, this is new. Labels displayed, labels hidden. Okay, I guess we want labels displayed. All right, here's the word cloud, which again, we might need to go to the individual level. But to start with, let's look at the fun word cloud. Okay. All right. So, couple words sticking out to me. One is stuck. That's a good word. Another one, some people mentioned adversary and adversarial. That's what we were talking about last week. Things like that. Let's see. Does anyone have the word explore on here? Situation unlikely. Navigate. Explore. There it is. I found it. Okay. So this is the main idea I was going for, is that if you do random things, you can help you explore. Let's see what if somebody wrote this down exactly and put it in some nice way. Okay. So unlikely to take the optimal actions when taking purely random actions. This is an argument why random is bad, right? I want an argument that random is good. Of course, this is the thing, right? Random is sort of, at the end of the day, it would be great if we could figure out the optimal thing and just do that. That would be non-random. Like if we learn that hit is better than stay, then we'll always hit and we'll do better. But this random stuff helps us get to that final conclusion. So this is an argument the opposite way. Navigate the solution space. This is one way to think about it. If you're always doing a deterministic strategy, you're sort of narrowing the space of possible things that can happen to you, right? If you always hit when you see a 20, you'll never learn that actually staying maybe is a better strategy. So by doing a random strategy, you can sort of you can explore the whole space and figure out what is good or bad. It's like imagine you're walking through the woods and you always stay on the same path. You might not notice that there's some cool, I don't know, what is cool in the woods these days? Some cool mushrooms that you will eat. This is like a European thing to go mushroom hunting. Okay. All right. So you got to navigate the solution space. Test out potential high rewards. This is a great way to say it. To explore. I don't know about the without bias. If you say that, you might make the statisticians angry. Okay. Okay. This is, so if you're thinking of it adversarially, then this is another way to think about why you want to do this stuff. If you have an adversary and you want to optimize in the face of an adversary, though how can you ruin the adversary's day? You will play random stuff. This is also relevant in games like rock, paper, scissors, right? Even if rock, paper, scissors was slightly tweaked, and like maybe you get more points if you win with rock, you still don't want to play rock every time, because then people will learn that you always play rock and beat you. So that's another reason to have random stuff. So this adversarial framework is another way to see that we want random policies. Okay, so you don't get stuck in a potential bad spot. Very nice. Okay. I think it's the opposite. We're not keeping the state space. If you always play the same thing, then you can keep the state space small, right? But you can always stay on the same narrow path. But by trying random stuff, you explore around and make a big state space. Okay. More exploration equals better. This is the right idea. But remember, more exploration, you don't want to maximize the amount of exploration. You want to have some kind of balance between exploring enough and finding good things and also choosing the best things, right? It's not like we want to try everything equally. We want to figure out what is the best and stick to that. Okay, so we're going to see how this exploring idea, which comes from random policies, how it ties into what we were doing earlier about these control policies, Q-learning and SARSA, that kind of thing. And I'll remind you, so when we started Bandits, we started with this little cartoon, which was saying, why is greedy bad? Why is greedy bad? And so there were two doors. I guess this was some joke about the academic system. But anyway, there were two doors. And if you choose the left door, you got 0. And then after that, the right door was somehow always positive. And if you were greedy and always picked what was the best door so far, you would get stuck into always picking the right door. And this is bad. You're not exploring enough. You should try the left door a little bit more often. And so we talked about lots of different ways to do this. There was this bandit situation. There were the upper confidence-bound bandits, which are really commonly used. There was the whole adversarial thing, which is a whole other way of thinking about it. And you really can do like your entire PhD on these bandit problems and things like that. It's a deep area of research. But the punchline is, you need to incorporate some randomness, you need to incorporate some exploring when you do these things, or you're going to get stuck on the bad door. And the easiest way that we're going to start with is this thing called epsilon-greedy exploration, which might have been mentioned already, which is what we're gonna make all our algorithms using this, and then for the final project, if you want to do something fancier, you can as well. So this is the simplest possible thing that you're going to need, at least for lab 3, which is on Thursday. You're going to need to know this epsilon-greedy thing, and I'll show you some examples today. And today's really going to be like kind of review, trying to help you get set up for lab 3 so you see what's going on, because it is quite a bit harder than lab 1 and lab 2, and it's more open-ended, and it's a lot closer to what the final project is going to be like. Okay, so we need the epsilon-greedy, and the epsilon-greedy says our policy is not going to be always do the same action A. It's going to be sometimes we do something random. And so here it's written in a kind of a funny way, which is saying, what is the probability of doing action A given you're in state S? Which is a perfectly fine way to write it down. But instead of saying, what is the probability of doing action A in state S, I think it's a little bit clearer mentally to write down, when you're in state S, what do you do and with what probabilities? So I'm going to rewrite this thing in that way. By the way, these are the notes from David Silver's course, which is a great course. It's all online. This is how I learned this material the first time I watched this course in like 2016. Okay, let's write it down my way. Okay, so this is greedy. Greedy is what we've done so far in the course. And greedy says, what do you do? What is the action at state S? So pi is the policy. And when you're at state S, what do you do? And greedy says, do the thing that maximizes the Q value, SA. We were QSA, okay. Argmax of A, of allowed actions from state S. So the greedy policy says, you're in state S, look at the value of all the different actions you could take, choose the action that is the best. Okay, and again, this is perfectly fine if Q was the perfect function. If we had an exact estimate and we knew the value everywhere, this would be the best thing to do, of course. And in fact, this is like half of the Bellman equation. But in reality, capital Q is some estimate for what is going on. We're not sure how good the left door is, how good the right door is. And so if you do this greedy thing, you're going to get locked in sometimes into a suboptimal situation. You're never going to explore around, and you're never going to find the right thing. So that's why greedy, even though it would be the right thing, sort of, if there was no randomness, we can't we can never escape that. And so we're going to do the epsilon-greedy. The epsilon-greedy. And this is the simplest possible way you can fix things to make them work out. Okay, and what is the epsilon-greedy? Now pi of S is no longer just one thing. Pi of S is some kind of probability distribution. Okay, and I'm going to write it like this. So in the same way that like a coin flip X is either +1 with probability 1/2 and -1 with probability 1/2, you can write out what the policy pi is, and it's no longer just one thing. It's a bunch of different things. It's a random variable, and that's why you could more accurately you could say pi of S given A. Pi of A given S is the probability to choose action A at state S. Why am I making a big deal about this stupid notation? I don't want you... In some textbooks, they write it like this. They say pi of S is a random variable. And in some, they say pi is the probabilities. And so depending on where you look, you'll have both. So you really got to keep your head screwed on straight on what they are. I guess, okay, let me write it out this way first. So pi of A given S is the probability. You could write pi of S equals action A with probability pi of A given S. And you could enumerate all of these. So you say A1, A2. So this is the translation between, I guess, the two notations. The one notation, pi of A given S, and the other one that says just what is pi of S. They're the same idea, written two ways. AN given S. Okay, that's one way to write it. In our case, we're doing the epsilon-greedy action. So the epsilon-greedy is like this. Most of the time, you're going to take the best possible action. So this is the greedy part. So we're going to do the argmax of A, of Q of SA, and we're going to do that with probability 1 minus epsilon. So we flip a coin. If epsilon is 10%, then 90% of the time we do the best thing. That is exactly the greedy policy. And then with the other epsilon percent, we're going to do something random. With probability equal epsilon, we do something totally random. And by totally random, I mean of the all possible choices, pick one uniformly at random. So that's one way to write it. I think this is the clearest way. 90% of the time, we do the best thing. 10% of the time, we do something totally at random. You could also write it like this. You could say, do the argmax Q of SA with probability equal 1 minus epsilon. And then you could split up this epsilon. You could split it up into epsilon over n events. So you could say with probability epsilon over n all the way up to with probability epsilon over n. And then you could write down all the actions. A1 all the way up to an. You can say, I'm going to do action A1 with probability epsilon over n, action an with probability epsilon over n. This is the situation where there are n possible actions you can do. Okay, so this is the epsilon greedy algorithm, and it's the simplest way to sort of do a little bit of exploration, but still have the idea of doing some exploiting. Most of the time you do the best thing, sometimes you explore. Hopefully that way your program learns, it explores enough actions it can figure out what's going on. Any questions or comments about this one, about the different ways to write it down or the notation? So if you compare to what is written in the thing, I find it a little bit more confusing, but now you can see what it is. Here's one thing that's a little funny. Why is there a 1 minus epsilon plus an epsilon over m? So first of all, I was calling it n. They're calling it m. But why did they do 1 minus epsilon plus epsilon over m? What's the deal with that? I don't have that anywhere on mine. Did I make a mistake? Let's put them side by side and let you guys think for a second so you can reconcile. This is like when you're reading math. This is like very often how it goes. You're like, I think it should be like this. And then you're like, wait, that's not how it is. What happened? Okay, what happened is I don't know where the note went. Okay, let me, I will let you think. So try to figure out where is this from. I'll wrestle with the computer here and we'll reconvene in a minute. Let me figure it out. Note, March 7th. Okay.
That's the probability that you want. So epsilon is the probability
Before they were using n for the a1 through an, they're not considering the first action, and then the second one they just say m is every action. And so you add that onto the top one as well to make it.
Okay, someone want to tell me why? Yeah.
They mean the same thing. It's just your probability of randomly picking your argmax is epsilon over m, so that's just adding that in.
Yes, exactly. Yeah. So they're both actually perfectly equivalent. And again, it's just this funny change of notation. And the reason is I have actually written down in my list of possible things that can happen, I've written down this optimal arm. It's written down twice. It's written down once as the 1 minus epsilon event, but it's also written down somewhere in this list, right? The best possible arm is one of these arms. And so I don't know, you can think about maybe it's this one, and then also somewhere in the middle, there's an epsilon over n. So there's two different ways I could choose this arm. That's the best arm. I could either choose it the 90% chance of picking the best arm, or I could choose it by chance in the exploring bit, and still by chance end up doing the right thing. So that's why there's a plus epsilon over m. If you want to write down the probability of choosing that particular arm, then the answer is 1 minus epsilon plus epsilon divided by m. And all the other arms, right, except for this arm, every other arm appears exactly once with chance epsilon over m, only in the sort of explore bit, never in the exploit phase. Okay, so that's epsilon greedy. Hopefully we have it right. Any questions or comments about the epsilon greedy so far? Okay, let's think a little bit more about the epsilon-greedy and how it works. And so I think we're going to go back to the simplest possible thing that we started with a long time ago, which is Monte Carlo policy iteration, right? So we talked about with Monte Carlo how you can evaluate a policy by just running the policy and seeing what happens. That is Monte Carlo policy evaluation. And then you can improve your policy by choosing a new policy, which is the epsilon-greedy with respect to the Q. And this is the little diagram that went with this. We also drew this a few times. Here, let's copy paste this into our notes so that we can scribble on it. So here it is. Okay. This is some other class coming up. Okay. Okay. So we also drew this kind of idea as this little loop of having policy evaluation, and policy improvement. And we have this loop of going back and forth. So if somebody gives you a policy, you can evaluate the policy by running it many times. That's policy evaluation. Policy improvement is when you take the values, somebody calculates the Q values, and you improve the policy by acting in a certain way with respect to that policy. And now we're saying, let's do the epsilon-greedy. So policy improvement will be, once we have the policy evaluated, we're going to use the epsilon-greedy. And once we have our improved policy, then we can evaluate it using, say, Monte Carlo evaluation. Okay, and the Monte Carlo evaluation was our simplest possible thing, where we said, you just run many episodes with respect to a certain policy, and then you see how they do, right? So if you want to know the value of some state, you just run many episodes starting at that state, you see where they end up, you see how much reward you got. Okay, and here is the picture in terms of this other kind of diagram where you think of doing steps where you evaluate and steps where you improve, evaluate, improve, and you hope that you converge to the Q star pi star, which is the optimal policy pi star and its Q value Q star. So star means optimal here. And you hope that as you do this cycle over and over again, you get closer and closer to the real thing. It's like value iteration. Okay. Why is this so important to know? Because in lab 3, you're going to be doing this. So let me open up lab 3 quickly. Is it here somewhere? Yeah, there it is. So in lab 3, we have this betting game again, right? So there's a gambler who can bet with, and he wins the bets with some probability P win, and he loses with some probability P lose. The new thing in lab 3 that is different than in lab 2, in lab 2 there was one value of P. So it was always 0.6 or something for the entire problem. In this one it changes. So every hand, before the hand is played, the gambler gets to see what is P win. And question 1 says, use a Monte Carlo method to evaluate a fixed policy. So if somebody tells you, I'm always going to bet $2 when the probability is 70% and I have $5 in my bank account, somebody specifies the bet sizes, you use the Monte Carlo method to figure out what is the value function, right? So for every possible state, find the value using Monte Carlo. And in Q1b, you're going to do policy improvement. So you're going to use this epsilon-greedy to improve the policy, right? So you take what you did in Q1a, that's one half of it. In Q1b, you do the other half, you try other things. This is exactly what we had written on the board before. And you should be able to find a really good bet size policy. So you should find the optimal amount to bet for every given state. Okay, and I made it open-ended. We're going to talk about TD in a second. I said you can use Monte Carlo or TD. And then over here, I said use TD, but of course you could do Monte Carlo too, and I will leave it up to you. This is the thing about, now that we're further in the course, there is no simple exact right answer. Things are going to be messy. You're going to have simulations. You're going to have to choose what epsilon is. That's going to be up to you. You're going to have to choose parameters in your thing. There is no one answer anymore. But that's what you're going to have to do in lab 2 or lab 3, question 1. Is this kind of loop for figuring out the optimal policy in a game like this. Any questions about that? Yeah.
Do we have to keep epsilon constant?
This is a fantastic question, and it's related to where we're going. In the next slide, I think I talk about this. Okay, let's skip ahead to where this is. So this is a thing called greedy in the limit with infinite exploration, also known as GLE, which is saying if you make epsilon, you shrink it down to 0 as you go. So the further you go, the lower epsilon is. Then you can achieve this thing where you visit every state and action pair infinitely many times. So the number of times you try each thing is infinity in the limit. And at the same time, your policy gets more and more greedy as you go, where at the end, sort of at time infinity, you are actually doing a greedy policy. Because that's what you would like to do. After you have perfect knowledge, you want to go perfectly greedy. So it is up to you to choose the epsilon going down to 0. And you will see that you can get better or worse performance tuning the epsilon. So that's part of what you're going to have to do in the lab is play around with this. We're going to have an example of this a little bit later, of seeing how we can mess around with this epsilon and see different kind of results we get. Okay. Yeah, great question. Yeah, we'll talk about this a little bit more as we go too. Any other questions or comments about that? Okay. So let's talk about improvements. This is like the core idea, right? So if this didn't make any sense, like everything else is going to be like building on this and just doing small tweaks to it to make it easier, to make it more efficient, to make it use less samples. And the first one is, okay, the way this is written, you're kind of thinking of this loop of policy evaluation and policy improvement. When you evaluate the policy, you can imagine running like 1,000 simulations. You say like, I have this policy in mind, let's try it 1,000,000 times and see how well it does. Then we'll have a good estimate for the Q function. Once we have a good estimate for the Q function, then we improve it with an epsilon greedy, and then we start over and do it again. But actually, one really easy improvement that you can make, which seems very counterintuitive, is to go to the following diagram, which is, again, from the textbook and from Nate Silver's course. And here, they have the arrows only going halfway. What do the arrows only going halfway mean? It means don't wait until you have a very good estimate for capital Q. So don't run 1,000,000 simulations, just run one simulation. And so your capital Q will be extremely noisy, right? When you do this, let's copy paste this in. So here's idea number 1, improvement. Idea number 1, don't wait. Don't wait for good data. This will say data, okay. And so it looks like this in the book. So the idea is only do one episode of policy evaluation, then update policy. Update policy by epsilon greedy. So sort of instead of waiting a long time, waiting for many simulations to finish and getting a really accurate Q, you just every time you run it, you have a slightly improved Q, just update your policy. And in fact, you'll see in the code when we run it, and we're going to do an example, the policy pi is just always taking the latest value of Q and using that to come up with what to do. So every time we make a small improvement to Q, we also simultaneously make a small improvement to our policy pi. So it's like we're going, instead of like waiting a long time, going here, do a lot of episodes, go here, do a lot of episodes. We're just going back and forth all the time. So every time we run an episode, we improve, and then we go back and forth, back and forth, back and forth. We don't wait until we have a good estimate. We are just doing this thing. And so that means that sometimes your Q value won't be a great estimate for what's going on, right? Because you've learned something about a certain state, and then you change the policy. Now the Q value is sort of like out of date. But it's still a faster way to get to Q star pi star, because you don't have to wait, right? You're not waiting for good data. You're just updating as you go. This is sort of like learning on the fly. Okay, so that's improvement idea number 1. Does the picture sort of make sense? I know they have this diagram in the book, and they have this like notion of like the arrow. What does it mean for the arrow to go the whole way or halfway? Okay. Improvement idea number 2 is instead of Monte Carlo, you could do TD. Improvement idea number 2. use TD. Okay, and I know it's been a while since we did this TD stuff. I want to see how much you remember. So I made another word cloud question where you tell me, what do you remember about TD? What's the difference? And what are the advantages of TD? Why would anybody want to do TD learning? Okay, yeah, let me give you a couple of minutes to refresh your memory on that. Feel free to look through your notes, and we'll reconvene in a few minutes.
My understanding is that it's based off of your prediction for your future.
That's good. I think I do. Yeah, we'll see. I think we'll be fine. Yeah, hopefully.
Case studies is also good. We can like guarantee function.
Because you are. I just have to write just waiting. But yeah. There's definitely soccer. You guys joined last time.
Yeah, we're almost there. I think we just have one more thing to
Nice.
and then
That's right.
we ended up spending, the other group didn't put any afterwards, so we got like the PH rate that does not happening.
Yeah.
But it's the end of the talk.
Like the amount of time you're looking into the future type thing.
A bit more math.
So you're basically. Yeah.
I just want to, I'm gonna
Like
switch.
you're doing Monte Carlo based off of your predicted patterns.
I think it should be fine. Once I can. Yeah.
That's the hope.
I didn't think they were changing like their requirements on the stuff like that.
What is
I
that?
think they're basically making it more open, so I think the area of emphasis is like kind of a thing.
Like, you have to, like, do electives. Core math or stat. Yeah. So it's less even less. Switch to math. Less math.
There's like some other stuff too that we're doing missing.
Yeah, that would be.
Yeah, it's like my understanding is that it's like half and half stat and investigate like all the probability stuff.
Yeah,
They never have time for it in like stat 2040 and 2050. And then it's like some like paradoxes. I don't know. It seems cool. The description seems pretty cool.
Yeah. You're also switching to it.
Congratulations.
I
I wish, but like, so that yeah, it doesn't really make a difference. Except for my master's offering. Yeah. I have a whole fiasco.
Okay, I think almost everybody has answered. Let's see what people think. Why would you do temporal difference versus Monte Carlo? Again, Monte Carlo. Many people, if you meet somebody on the street, they might know what Monte Carlo is, but they probably won't know what temporal difference learning is. So it's more complicated in some sense, but it's also simpler in some sense. So it really is kind of. In some sense, it's better. In some sense, it's worse. Okay. So some people said it is faster, and one sense in which it's faster is you sort of need less simulations to make it work. So that's a nice thing. So faster is a good one. Incremental, what a great word. So in Monte Carlo, you wait all the way till the end of the episode before you do any learning, before you update anything. you drive your car and you wait until you crash the car to learn, oh wait, don't do that. In temporal difference learning, you're learning all the time. You're learning little bit by little bit. You kind of like have little signals that help you learn little by little rather than waiting all the way till the end of something to happen. So let's see. These are great. Let's see what people said specifically. If there's any nice answers in here. Straight to policy updating. So again, we said in improvement number 1, we said, look, the proper thing to do would be to do 1 million samples for any policy. Really learn the Q function quite well, and then update. And then we said, oh, idea number 1, just do 1 episode, right? And then learn a little bit from that 1 episode. And in the temporal difference learning, you don't even wait till the end of the episode, right? You just do 1 little step, and then you learn something. So it has this incremental idea that is mentioned here. So you're going straight to the policy updating. After every single step, you do something. Can't remember, very honest response. That's great. We get updates more frequently, which allows for faster convergence. So very nice. Less computation. So one really nice thing about temporal difference learning is you don't have to write down everything that happened. In Monte Carlo, you have to write down all the states you visited so that when you finally finish the episode, you can go back and update them. So you sort of need a bigger memory to write everything down. In temporal difference learning, you just like learn a little bit, then you forget what happened, you've already learned from that, and you keep going. So it's actually easier to write the code. And in the example I did, I will confess, I only run up the temporal difference learning example because the Monte Carlo is annoying to write exactly because of this. You have to write the memory, then you have to store all the states that you saw, and things like that. So you don't need to wait, you go right away. Okay, great. Yeah, this is a very nice one. TD updates value estimates more often mid-episode, so in the middle of an episode, and therefore it can converge faster than MC. You learn as you go. These are great answers. Okay, very nice. I will say, in both MC and in TD, there's this alpha and gamma thing. Let's talk about that so that you can see what they are. So let me write down exactly what the difference is. And so before I write down the TD rule, let me remind you, what is the MC learning rule? So what is the Monte Carlo learning rule? And the rule is like this. You have some state SA, and you run the episode, and you update the value of Q of SA, like so. You take what it was before, and you add on some alpha, and then I'm going to write it like this, G minus Q of SA. Where G here is G equals the return. G equals actual return we saw by the end of the episode. At the end of the episode. So for example, if you're playing a game of chess, you play pawn e4, that's your opening move, and then you wait until the end of the game, you say, did I win or lose the game? And then you say, oh, I won the game, I should play pawn e4 more often. Okay? Or if you lose the game, you say, oh, maybe I'll switch to d4. You switch to a different opening move. So you wait until the actual thing, and then you update that. And you have to remember all the S's and A's you saw along the way. You do this for every SA we visited. So for every state we visited and every action we took along our trajectory, along our path, do this update. And it's kind of annoying, we have to write them all down, and then we have to go back and update them all at the end. In the temporal difference learning, very similar thing, and you can think of, we're just replacing this G with an estimate for G. So with the temporal difference learning rule, the TD learning rule. Okay, and I will say, let me say this is SARSA. This is the SARSA learning rule. We're going to see some variations on this that are all very similar, replacing the G with some kind of estimate. But the SARSA rule is like this. Q of SA, right, becomes what it was before, plus alpha, and then we don't wait until the end of the episode. We just wait one more step. And we see what rewards did we get in that one step. And then we do plus gamma times Q of S prime A prime. And that's minus Q of SA. And so you can think of this whole thing here. This is an estimate for G. So we take one step, we're at the state SA, and in the textbook they draw this little diagram. They say, we are at the state S, we take the action A, We're at S, we take the action A. We observe some reward R. So by taking the action A, we got some reward R. And then we say, okay, now what is our next state? What is our next state and our next action? So we get to some new state and we have some new action. That's why it's called SARSA, because you have the state and action you're in, the reward you saw, and then you have to figure out what is the new state you're in and the new action you would take. And this is the SARSA update rule. You update the Q function to move in that direction. Okay, and again, both of them are a little bit slippery because of this alpha parameter, which we've talked about, and is something in your actual lab, you're going to have to decide what alpha is. Like you're going to put in alpha equals 0.1. You can also change alpha as you go. It's a good idea to sometimes have a big alpha earlier on and a small alpha later on, so that'll be something that is up to you. We'll see that in the example as well, that changing this alpha can really help you get better results by making it smaller as you go. And in Monte Carlo, if alpha is exactly alpha equals 1 over the number of visits, that's exactly the classical Monte Carlo, and we sort of generalize that by having alpha be some arbitrary number. Once you start doing these TD learning stuff, you know, it's some abstract thing. It's like the amount you're moving, right? The amount you're incorporating new information into your estimate for Q. But that's the TD learning rule. Okay, so I think this is all sort of review, but it has been a while, so feel free to ask. Any questions or comments so far at this point about the rules, or about SARSA? Okay, I've mentioned it several times. Let's see an example, and this is the example that we had. We actually opened this example right before we started Bandits 2 weeks ago now, which is the gambler's problem. Let me run everything. Or actually, okay, let's leave it. So, and remember, the nice thing about the gambler's problem, why do we keep doing the gambler's problem for every single problem, is because the gambler's problem has this nice exact solution. So here is the gambler's problem with $13. So the gambler is going to leave the casino if they ever get to $13, and they go broke if they're ever at $0. This is a casino that I think has a 40% chance of winning every bet. 30%. So P heads is 0.3. So every time you make a bet, you only have a 30% chance of winning and a 70% chance of losing. So what is the optimal strategy to try to get to $13 before you go broke? Just always bet all your money, right? So bet the maximum amount at every step. And value iteration, what we did in the first few weeks of the course, finds this perfectly if you know the rules of the game, right? So if you know all the information, you know how the casino works, you can calculate this, and this is the value function. And okay, then we did TD learning. So we did this last time. Let's run everything. And when we did TD learning, we only use the next state function. So this is very general. We don't know the rules of the game. We just have observations. And last time, when we originally did it, I did it with the pure greedy solution. So I said, if we do it with the greedy function, so let me put in greedy. Here is greedy. This is reminding you what happened last time. We're going to have epsilon-greedy in a second, but I'm going to show you that it doesn't work with greedy. Hopefully this will run. Okay. Okay, what does it not like? I see. Okay, I have to change it in 2 spots. Let's change it in 2 spots. All right, epsilon-greedy, get rid of the epsilon-greedy. Let's do greedy for now, and we'll do epsilon-greedy in 1 second. Okay, so what's going on here? Again, this is running through the simulation. We take our current action is the greedy answer given our Q, and then we sample a new state and a new action just from this gambler's problem next state function. So we don't know the rules of the game. All we know is we took an action and we arrive at some new state, and we got some amount of reward. In the gambler's problem, the reward is always 0 because you can only win final terminal prizes. You only get a reward if you actually escape the casino. In your problem that you'll do in question 1 on lab 3, there are some rewards because there's the savings account. So if you have a bet that's big enough to put money in the savings account, your reward can be whatever would go into the savings account. Okay, so we sample the current action and the state. We get the new action, and then here is the SARSA update rule. Reward plus Q star minus Q star of current state, current action. This is exactly the SARSA rule. Here, gamma equals 1. Gamma is this like discounting rate. This is an undiscounted thing, so gamma equals 1. And if you run this, okay, it seems like great. We're doing SARSA perfectly. We did exactly what it said in the textbook, and you will find out that it outputs always bet $1. And when you always bet $1, you have terrible, terrible value. So even if you start with like $7, you have a close to 0% chance of leaving the casino. And the error is huge. The error is huge. So you're off by 40% from the true answer. And the reason is, if you do a greedy situation, then you will never find the right answer. You sort of get locked into the wrong door. You always choose the right door, where the left door was the right answer. So to get away from this, you can do an epsilon-greedy. And so all I'm going to do is take my sampling of the current action. So given the Q function, how do you find the next action? Don't do greedy, do epsilon-greedy. And so that's what this line is. So let's put that one in instead. Current action, we're going to do epsilon-greedy, and that way we'll have some exploration, and the exploration will allow us to find the right answers. Okay, so I also want epsilon-greedy over here. Let's do that as well, which I think is this one. New action equals gambler's problem epsilon-greedy with the Q star. So this inputs the Q and outputs the thing. And if you look at the code, I guess I have to go up and run it as well. You'll see exactly what it is. The epsilon-greedy, it does what I started the class with today. So it makes a probability epsilon event. This is something that is either true or false. It is true with probability epsilon, and it is false with probability 1 minus epsilon. And if that is true, then we just pick a pure random thing. So if the probability epsilon event is true, then just go pure random. Otherwise, if it's not, then we go pure greedy. And so the pure greedy is exactly what we started the class with today. That's the greedy algorithm. There's also some little extra stuff, which is what happens if you're broke already or you're at the final situation. So there's some extra little things there. Like these are like the default answers that you will do. Okay, so that's the epsilon-greedy. And now when we run it, let's see what happens. Gambler's problem with SARSA. With epsilon-greedy, it gives you an error because something is wrong. Yes, okay, you can't have a line like that in Python. Okay, and again, I'm running 10,000 iterations here, so 10,000 samples, and we're learning after every single step, and you have some final function that looks like this. Okay, this is still quite bad. Oh, you have to maybe have to rerun. Did I put epsilon-greedy everywhere? Okay, epsilon-greedy, learning rate, epsilon, epsilon. All right, did this work? Let's run it. Again, okay, what does it not like? Did I mess with the... Oh no. Okay, it doesn't like this one. Okay, let's try it, let's try this. I might have misclicked something here. Okay, let's do some fun debugging. Okay, return this int if low is greater than high. Okay, maybe I put this thing in wrong. Epsilon-greedy, epsilon at the end, epsilon-greedy. Okay, look, you guys see the bug? This is good practice. What is going on with these two things? That's new state. This is current action and new action. There's something wrong about these. Can you guys figure it out? I'll let you. This is a good practice for your debugging skills. There's something horribly wrong. Yeah?
Your arguments are wrong.
Yes, that's right. One of them has epsilon at the end. One of them has epsilon not at the end. So one of them is wrong. Okay, which one is wrong? And so that's why I'm getting this bug that makes no sense, because I told it, I fed in something like epsilon as the state or something. So this is, if you get like totally crazy errors and you're like, what the hell is going on? Sometimes it's something like this where something is going wrong. If you want to be absolutely sure in Python and never make this bug, one nice thing in Python, when you call functions, you can put in like epsilon equals epsilon, where this epsilon means the thing that I'm calling epsilon in the function, and this epsilon means the thing I'm calling epsilon in my actual loop. And then you'll be sure that it puts the things in the right spots. So if you just type them in order, you have to get the order exactly right. If you give them names, then Python will assign them to the things with the right names, and then you can put them out of order and it'll still work. So that's a good pro tip. Let's solve it for now by just putting them in the right order. So let me go to the gambler's problem epsilon. It looks like epsilon is supposed to be at the end. So you're supposed to give me S, the state we're in, Q, the array with our Q values, N target, that's like where we want to exit, and epsilon. S, Q, N target, epsilon. And what did I actually give you? Here's current state Q n epsilon. That one's right? Okay. And so must be the other one that's wrong. N Q, this is epsilon and target should be the other way around. Okay, very nice. Comma, epsilon. All right. The other thing you got to do is spell epsilon right. Okay, let's see if it works this time. Hey, okay. So, this time we got an answer. This looks a little better. Of course, can you spot something that doesn't make any sense about our output here? Thinking in terms of real life. What is the major bug you see, or the major thing that is not physical to real life that you're seeing in our value function here? Yeah.
We increase the value in our bank account, but our value goes down.
That's right. Look, this is saying that if you have $7, you're more likely to exit the casino than if you have $8, right? Having $7 is better than having $8. So that's not right. Of course, this is Monte Carlo, or like TD learning. You learn with randomness. You're going to get a random answer at the end of the day. So what this is indicating to me is that we should run more samples. We should tune those epsilon values. We should tune the learning rate to try to make this better. Let's see how big our error is. So right now, this is our optimal bet size. Again, it's not saying always bet all in. It has some problems, like here it thinks we should bet only $1. So when we have $4, it says, I think you should bet $1, which we know is not right. And we can see what the error is in this problem. And you can see it's actually not so bad. So it's off by about 10%. So here it's off by like 9%, here it's off by 6%. So it's getting pretty close. If we ran it forever and ever, this would hopefully shrink down to 0. And one way to make sure, there are theorems that tell you when does the thing shrink to 0. I'll give you one of the theorems now for people who are more theoretically minded. And that's where this glee thing comes in. So if you are greedy in the limit with infinite exploration, so if you explore all the states infinitely many times, and you become greedy as you go, for example, this epsilon is like 1 over k, then you will have some kind of convergence. So this is saying for Monte Carlo that you will converge. Very similar results work for TD. So what we got to do here is tune these values of epsilon and the learning rate, and we can try to improve it. So let's do a little bit of that now. This is the kind of thing you guys will be doing. So here I have epsilon. I have it 2 divided by the square root of the episode number. So this is, again, shrinking down to 0 as you go, but kind of at a slow rate. So I could try making it go a little bit. So let's see what would happen if I just make it divided by epsilon. This is making epsilon smaller. Instead of dividing by the number of times I've done it by the square root of that. I've done it by dividing by what episode we're on. So dividing by a bigger number, that should be more greedy. I made it more greedy. Let's see if that helps. So I made it more greedy. Rerun it. Let's check out our answer. Okay, so, it looks like we've gotten rid of that bump. Optimal bet size not looking as good. Ooh, and we have a lot bigger of an error. So this is too greedy. I went too greedy. I'm not getting good results. Let me go less greedy. And in fact, there is some sense in which the exponent of 1/3 is good. I will. This is related to the class where we calculated that the number of times you want to explore is n to the 2/3. Let's make it to the 1/3. That's exploring a lot more. Let's explore a lot more. Okay, and look at that. Our optimal bet size. We're saying, look at these big bets are good. We've explored more. Again, it's not purely monotone, but we still have some things. And now we have an error of like 12%. I think I might have started with the pre-optimized one. I was messing around with this yesterday, and maybe it's saved when I didn't want it to. The other thing you can mess around with is the learning rate. So let's make the learning rate, right? This is the alpha value that you're tuning, and you can change this as well. So right now, let's make it a little bit bigger. Actually, we can just multiply by 10. Why don't we do that and see what happens? So if you multiply it by 10, okay, here we go. We got something like this. This doesn't look so good to me. Oh yeah, lots of big error. Why don't we make it go down to 0 a little bit slower? So you can change this to some power. Let's try to the 1/3 power again. That's another fun thing you can do. You can try different powers and different schedules of how you do it. So this will make the learning rate bigger. Oh, okay. So this found a terrible value function, but it found a really good optimal bet size, which is very confusing to me. What's going on here? It found the right thing. Okay, maybe what I need to do is make it, let's put this back to 1. and try this. Okay, this is looking good. Okay, and again, we're back down to around 10% error here. So by playing with the learning rate and the epsilon, you can get all sorts of different things happening, and you can see, kind of mess with it. If you have some intuition about the problem, like if you know that it shouldn't go down, those are like hints you can use. Okay, so this is the code with SARSA. The main, I guess, thing to take away is that this is the update rule. That's what was written on the board a minute ago. And you have this choice of what should epsilon be and what should the learning rate be, and those are both important. And you have to mess with them and see what works. I think what I'm going to do for lab 3 is I'm going to make a leaderboard with just like, how good is your gambler? You're going to send the gambler to the casino. Whoever's gambler is the best will have the highest score on the leaderboard. That's what's going to happen in the final project as well. So by messing with these, you can try to make better or worse gamblers. See if you get better or worse results. Yeah?
Is there any sort of like process to picking those rates? Like, is there some sort of guide, or is it just totally like, guess, hope it's right?
I think you basically guess and hope it's right, and you try to diagnose problems.
Okay.
Like one possible problem is getting stuck in a suboptimal state, getting stuck on the right door. And if you see that happening, you should think, oh, I got to increase the epsilon, increase the amount we do it. Another possible thing is like, oh, it's not changing much. Like it's not, we're running all these simulations and it's not changing very much. That probably means your learning rate is too small. Make your learning rate a bit bigger. But this is like a common thing in machine learning, like all these little things. It's hard to know how it works because it's not an algorithm that always outputs the right answer. It gets closer as you go, and like how long you have to go, nobody knows. So yeah, you're essentially right. You guess and check. Yeah.
Couldn't you do a similar thing and make a program that learns what the best epsilon is then?
Yeah, so and so some people do something, it's called hyperparameter search. So they try a bunch of different epsilons and you run it. You could also replace this whole epsilon thing with some more complicated bandit algorithm. So you could say like, instead of trying them all equally, let's like try the promising ones, like this kind of thing, right? Then your code will get more complicated. So I do recommend you stick with this epsilon thing and just try it. If you want to make a loop and say like, I'm just going to try a bunch of different epsilon values, that's great too. So that's fine. Another thing you could do is you could run more episodes. So the number of episodes here, I think I did 1,000. I did 10,000. That took 2 seconds. If I do 100,000, that should take like 20 seconds. That's not bad. So let's run that and hopefully this will work. And now, you know, the things that I typed in, those like epsilons and alphas, those were functions of how many episodes. So what you get, will it be better? Okay, this is like pretty good. But again, it's sort of like not doing great over here. You could probably mess with it and get better results. But this is looking a lot better. So yeah, this is like the hard part of real life stuff. I wanted to put some problems like this in because these are like the real life problems. Like in real life, you don't know what the answer is. You don't know what is the best epsilon. There is no one answer. You just have to try it and deal with it. So that's what you have to do. Okay. Questions or comments about this SARSA thing? Okay, there is one alternative to SARSA that you should know, which is called Q-learning. And in Q-learning, it's over here, the Q-learning update rule. In Q-learning, we changed the update rule. Okay. So, okay, yeah, I have a nice video from that video series we've been following with the Q-learning, and I'm going to show you that, and then we're going to discuss it and write down what it is, and we're going to see one fun example with the Q-learning. Okay, let me open this up and get this going.
Once everything's perfectly organized, I'll start working on my thesis.
Trade-off. Okay.
Okay. So here it is. And again, this is a great video series to review everything we're doing so far. So this whole video is on temporal difference learning. When we first learned temporal difference learning, we started with some stuff from the beginning. Now we're doing some stuff near the end. If you completely forgot what temporal difference learning is, this is a great way to review what it is. Okay, but here he's going to explain to us what is Q-learning. Q-learning.
At this point, we're in a really convenient position to learn 2 other algorithms. The first is Q-learning. To understand this, I'll pose it as an adjustment from one-step TD control. It's easy to extend it to n steps. The notation is just heavier. Okay, so the primary adjustment is to the target. In one-step TD, the target is this. Remember, the target is what estimates are moved towards on each update. Now in Q-learning, the target gets changed to this. What's happening here is, instead of using the action value of the upcoming state action pair to approximate the future rewards, we are using the max action value over all actions in the next state. And that, in fact, makes this an off-policy method. That's because the max operator is...
Okay, let me explain what he's saying here. So this is what I called R plus gamma Q. There's some notation here with the T plus 1s and the M's. I was just calling them S and S prime to keep the notation simple. Of course, when you actually run the program, you need to know where things are. So this is like a little bit more detailed. And all we're doing is we're saying instead of sampling some A prime, we're going to take the maximum value. So let me write that down in our thing. So I had R plus gamma Q of S prime A prime. That's the SARSA rule because you sample SAR S prime A prime. The Q-learning rule, very similar thing. So it'll start out exactly the same. Let me see, can I move this over? Move this over. I'll move that over here. Put that next to SARSA, because that was SARSA. For Q-learning, and again, I think Q-learning is a terrible name. Everything we're doing is learning Q. So I don't know why this one is called Q-learning and the other one's not. But similar beginning, and all we do is we replace with R plus gamma times Q. We replace that with R plus gamma times the maximum value of A, of Q of S prime A. And maybe I shouldn't call it A. Let's call it A tilde. Let's call it A tilde, so we don't mix up our different things. Okay. Minus Q of SA. Okay, and so what is this doing? Instead of sampling, so in SARSA, we move to some new state S prime, we sample some new action A prime. In Q-learning, we don't sample the next action. We say, what would be the best possible action? Let's learn in terms of that. And so if you were going to draw a diagram for this, the diagram I think in the textbook looks like this. So you have S, you have A, you get some reward, you move to some new state S prime, but you don't get a new A. What you do is you take the maximum. And they draw this like a little fan out tree. They say maximum or something here, max. Okay, so of all the possible actions you could take, what would happen if you chose the best one? And this is called, sometimes some people call this an off-policy method. Off-policy learning. And the reason it's called off-policy is because this maximum is representing doing greedy actions, right? If you always did greedy actions, this is what you would do. So in fact, if you did SARSA and you said, I'm going to do purely greedy, then SARSA and Q-learning are the same. But of course we know that purely greedy can't work. You have to do some exploration. And by doing this mixture of having the actual policy be doing epsilon-greedy and exploring, and then in this just this one learning step, we sort of do greedy learning. I'll put that in quotes. Greedy learning. That's like a mixture of two policies. One policy where you're exploring around, that's the actual policy you're following S, and then this is the one you're learning about. And that's called off-policy learning, when your policy that you're exploring around with is different than the one you're learning about. So we're learning about this greedy policy even though we're doing this exploring policy. That's Q-learning. There's another one called expected SARSA, which is very similar feel. You're going to see in a second that instead of doing a maximum, it's going to be an expected value here. But questions or comments about this one? I guess I can show you in our code. I have this one coded up. So I can show you the difference, SARSA and Q-learning. So all you do here is instead of doing this, Q star, it's the learning rate, it's the reward plus a V star. And what is V star? V star is the maximum of the Q star. And you can see here, one nice thing is I don't have to sample the new action, right? I just take the maximum over all possible actions. I don't have to worry about like running an epsilon-greedy or anything like that. So the code is a bit simpler, and we're moving Q star towards V star in this situation. So for me, this is like incorporating the Bellman equation more directly. Let's see what this one looks like. And I guess let's go back down to 10,000 here. I guess I messed the learning parameters up, so let's see if it does better or worse. Okay, actually, why don't, to have an apples to apples comparison, with everything set up before, this was like 0.12, and let's leave everything the same and see how Q-learning compares. Okay, you'll notice it's a bit slower. because it has to do the maximum, right? We're running hundreds and hundreds of operations of computing the maximum, and so it can be a bit slower. But look at this, very nice result. We're seeing the large bets for the most part, still a couple small bets over here we haven't figured out yet. And our error is only 8% here. So it got a little bit better. So the Q-learning sometimes is a little bit slower, but usually is better. You're kind of learning more quickly. You're reducing one sort of source of randomness in your algorithm, right? So instead of choosing a random action as your new action, you're looking at the best possible action, so that helps. Another thing you can do is called expected SARSA. I'll show that in a second. Maybe I'll pause here. Any questions about the Q-learning? Okay, let's see the expected SARSA. Actually, why don't I'll just write down the formula, and then I'll tell you. So that's Q-learning. You can also do expected SARSA is another one. So this was Q-learning, which is, I guess, is SARSMax. If you're going to make a little acronym for it, is Q-learning is actually SARSMax, and then there's expected SARSA. Expected SARSA. Okay, I'm going to do Q of SA. It's going to become Q of SA plus alpha. And we're going to do R plus, we're not going to do the maximum. So over here, we chose one action, we sampled it, we chose one. Over here, we did the maximum. And over here, we're going to say instead of choosing one, we're going to do the expected value over all actions. So it's going to be the expected value over alpha tilde sampled according to the policy pi. Remember, the policy pi is random now, and that's a crucial part of everything we're doing, of Q of S prime, and then this A tilde. It's going to go right there. Okay, so we sample the thing, minus Q of SA. Okay. And so what this does is it's somewhere in between the maximum and choosing just one. We're averaging over all of them. And to do this, you need to compute an average. So it is even more work. But as the picture would go, it would be like this. S, action A, reward R, get the state S prime, and then you average. So of all the possible actions you take the mean. So it's SARS mean. I don't know. SARS E. You got to come up with your own name. They call it expected SARSA. And this is another alternative you can use. That, again, this will basically perform strictly better than regular SARSA, because SARSA will sort of choose an action A prime randomly, and you're sort of saying, what would happen if I just looked at all the possibilities that you can do it? But it will be slower, because you have to do this average. So it's up to you to decide to try different things and see what's working and not working. And it is different than this one. This is purely on policy. This is only ever learning about the policy pi, whereas this one involves this maximum step over here. Questions or comments about this stuff? Yeah.
Is there still the gamma?
There's still the gamma. I forgot the gamma. Thank you. Yes. So gamma is this discounting factor. In all our problems, gamma has been 1, so I sometimes forget to write it. Great comment. Anyone else? Okay. To finish off here, I'm going to show you from this video, they have a nice little example of Q-learning versus SARSA. Here is expected SARSA, and this is also from the textbook. It's called the cliff walking example. I'm going to let him describe the cliff walking example and show you a couple samples of it, and I'm going to have you guys vote on what do you think the difference between Q-learning and SARSA will be and which one will do better. But here is cliff walking, which is another type of problem.
Visually. The first example is called cliff walking. For animation purposes, my version is a little different from Sutton and Bardo's. Okay, as is typical, it involves a grid where we start here and want to get here, which ends the episode. We have actions like these available to us, which deterministically shift the state to the neighboring state. And this is the cliff. If the agent moves into it, they get a reward of -100 and the episode ends. Otherwise, all transitions yield a reward of -1, and there's no discounting. So we'd like to get to the goal state as fast as possible while avoiding the cliff.
Okay, so this is the grid world example, right? This is like the Roomba. The Roomba starts here. The Roomba wants to get to here. Except we've added in a new thing to the Roomba. Before, the Roomba was getting hit on the head by the newspaper every step. That's a reward of -1 for every step, right? To try to encourage him to get out of the maze faster. But this time, there's also a cliff. And if the Roomba ever touches the cliff, then we like kick the Roomba or something. We like do something really nasty to the Roomba. Oh, it's like those videos with those like four-legged dogs where they're like kicking it all the time. We really horribly mess up the Roomba if it steps on the cliff, and we put it back. We're like, bad Roomba, and we put it back over there. And the Roomba, of course, has no idea where anything is. It's just like, I don't know what to do. Like, I will try to move up when I'm here, or what do I do? And the Roomba has to try to learn to go from S to G as fast as possible. Okay, there is a tension here, right? Because the Roomba could choose to learn the safe path, which is to go all the way up, then over, then out. Or it could learn to go the fastest path, which is like this. But the problem is the fastest path is sort of near the cliff. So if it's going to do the fastest path, it has to learn pretty confidently, I know where the cliff is and I know not to step there. That's the interesting thing in this cliff walking example. The best way is also the most dangerous way in some way. Like you have to go near the cliff to like optimize. Like if the cliff was on the other side, it would be a very boring problem. You just do the like optimal route, but the cliff is near the optimal path. Does everyone understand the setup? He's going to show us some examples of what's going to happen as well.
In fact, this is the optimal path.
Okay.
Now for all episodes, we'll be using an epsilon of 0.1 and an alpha of 0.5. We'll be keeping score here where the horizontal axis is m, the number of episodes processed. And the vertical axis is the sum of rewards, which is G0. So when we run SARSA for the first time, we get a pretty terrible sum of rewards. But we'll get better. Let's try again, and again, and again, and again. In fact, let's just do it many more times. After we've done so, this is what a typical episode looks like.
Okay, so he did SARSA. Every single green dot over here is an episode of SARSA, of running it. Of course, it starts out completely randomly, but as it goes, every step it's learning a little bit, right? It's like, oh, this was a good step. Like I'm closer to where I want to go. I'm improving my value. And you can see over time, it's doing better and better. And sort of after 140 episodes over here, which is 140 episodes is many steps, right? But after 140 episodes, it's kind of not falling off the cliff anymore, right? The cliff is at minus 100, and sort of near the end here, it randomly fell off the cliff here. But other than that, it's mostly learned to not fall off the cliff. And the way it's learned to do that is to go all the way up and go down. So it's found the safe route. What he's about to do is show you Q learning. And in Q learning, again, very similar to SARSA, except you do this maximum over the actions. And I want you guys to see, when I ran it before, you saw that Q learning was a little bit different than SARSA. I want you to think about what would happen with Q learning in this particular example. Is it going to do better or worse than SARSA? And we're going to have a little vote here. You can tell me what you think. Take a few minutes, compare these two things, and think about it in the context of the cliff walking. What's the difference between these two things in the cliff walking? And it's very closely related to these big ideas in the course, like exploring and exploiting, that kind of thing. What is better on the cliff walking problem? So which one do you think will do better? If you don't know, you can pick randomly. But take a few minutes and definitely chat with your neighbors. This is a hard one.
I definitely think it's SARSA. Because at the Q learning, we'll always try give higher value to positions that have highest value. So it will value it'll value the positions beside the cliff higher. So it'll go there. But because we have a constant epsilon, we have like a 1 in 10 chance of performing a random action, which has a decent chance of just sending us off the cliff. So Q learning will try to go beside the cliff, but our exploring thing is going to get us out of this problem.
Just keep exploring and just keep hopping off.
Yeah, if we reduced epsilon over time, I think it would do better.
Said maybe it's the opposite.
Did we do this? Yeah, I just did it on the video. And also like the thing that we did before Q learning was
Okay, people are quiet. Maybe I'll just stop the timer now. And let's see what you said. Let's reveal. Okay, 9 people think Q learning does better. 7 people think SARSA does better. The right answer is both are better. What? Why are both better? Okay, let's watch and find out. So we're going to find
Now,
out.
to evaluate the algorithm, we should rerun it, say, 400 times.
Okay, yeah. So
In
so
that
this
case,
is
the
average
average sum
finding
of
the average
rewards looks like
experience
this.
of SARSA by rerunning it many times.
Naturally,
So there's
we can
SARSA.
also plot Q-learning,
Okay.
which is quite a bit worse. So what's happening?
Okay, so Q-learning, when you run it, is doing a little bit worse. I will also let him explain what the path
It comes down to
is.
this. In the typical case, SARSA is executing this path, whereas Q-learning is executing this, which
Okay, so this looks like a better path than this. Like, to me, the orange path is better than the green path. So, like, if I had two Roombas, a green Roomba and an orange Roomba, I would say the orange Roomba is better. So why is it that the Q-learning gets a worse reward than the SARSA? Does anyone know? Yeah.
Keeping our epsilon constant, so we have a random chance to just end up off the cliff.
That's right. That's right. So because we're doing epsilon-greedy, and we're not doing purely greedy, we are not actually executing the best path every time. So when the Roomba goes, it's always deciding a 10% chance it's going somewhere random. And so when you have a 10% chance of going somewhere random, this orange path is actually a worse path than the green path because you have a 10% chance of falling off the cliff. Actually, I guess not 10%, a 2.5% chance of accidentally stepping down. But you have that at every step. So you have a 2.5% plus 2.5% all the way up to here. So you have like a 20% chance of falling off the cliff at some point, and that little chance of falling off the cliff makes this path too risky compared to that path. But you see, it's completely dependent on what epsilon is. If you made epsilon smaller, then this path would be better than the green path, right? So the smaller you make epsilon, the better the orange path will be. Of course, SARSA takes this all into account because when SARSA samples its next step, this is the thing about SARSA, SARSA actually samples the next action. So when it samples the next action, it will be baked into this sample, will be the epsilon-greedy. And so when you change epsilon, SARSA itself will actually find the better path. So like the green path that was found is optimal for an epsilon of 10%. If you make epsilon smaller, then the SARSA would actually find the orange path too. So this makes it seem like Q-learning is just plain worse, which is a reasonable conclusion. And like, if you selected Q-learning is worse, like you got the right answer. I would also argue that Q-learning is better because there's one simple thing you can do to make it so that the final answer of the Q-learning is better than the final answer of the SARSA. So imagine you run this whole thing, you've trained your Roombas. What can you do to make the Q-learning Roomba better than the SARSA Roomba? Yeah.
Just get rid of the epsilon.
That's right. So after the whole point of the epsilon is to just explore around. Once you've done exploring and you're like ready to ship your Roomba to customers around the world, you should probably set the epsilon to 0 before you put them in people's houses and they go around crazy, right? Like once they know the right thing to do, there's no point in having an epsilon anymore. The epsilon is just a tool to do throughout learning. You want to end sort of with epsilon equals 0. So when you submit your submissions for Lab 3 and for the final project, you can learn with epsilon, and then for your final submission, make epsilon 0. Or at least make it extremely small, right? You want to shrink epsilon as you go. In this one, he chose epsilon equals 0.1 constant. Choosing epsilon going down to 0 would be a better choice. And the Q-learning here would get the exact right answer if you choose epsilon equals 0. Okay, did I want to say anything else? Questions or comments about any of that? I'll say in the rest of the video, he does expected
Due to the
SARSA as
epsilon
well,
chance
and shows you
different.
what this does.
Its most typical path.
So expected
at the end
SARSA
is this.
does even better than SARSA and
Basically,
finds some middle
expected
path.
SARSA on a per episode
so there's all sorts
basis
of
is a
trade-offs
more
here. Even a
efficient
simple
version
problem
of
like this.
SARSA.
You know,
Again, it can be
it's,
understood by the difference in
when
targets.
you're actually programming it, there's a lot
For
of choices you have
SARSA,
to make.
we
What is
know
epsilon?
that
Do you
this
change it at the
action
end?
comes
How
from
do
the
you change
policy
learning rate?
distribution.
What do you do?
In
There's all sorts of
expected
things you have to do,
SARSA,
and
we are
that's what
just
your
using that distribution
lab and
directly
final
to
project will be like.
calculate the.
Okay, I think we'll stop there. I'll be around for a few minutes if people have questions. Otherwise, see you guys on Thursday, and make sure you bring your laptop and have read the problems. You can also work in partners for this lab, so feel free to talk to a partner beforehand. And see you then.